Okay, inverses. Probably the easiest thing about inverses, and this will work several different ways, or have several different meanings, is that to find an inverse, you switch x and y. And if you could remember that as the main thing with inverses, like that covers most of what we want to talk about with inverses. So I like to say that first. Inverses means switch x and y. Have we done this already?
I feel like we've done something like this.
Have we done it this year, or did you do it in Algebra 1?
Earlier this year we did like.
I think we did.
Yes.
So inverses means switch x and y.
I think it was when we were working with like a parabola or something like that.
Yes.
And like actually valuing that kind of stuff.
In fact, let's start with a parabola. Maybe not the standard parabola, maybe one that's been shifted a little bit. How do we tell if that thing is a function? So I'm going way back now. Yes. Jackson threw his yawn, just like does a quick. Yes, vertical line test. If it passes the vertical line test, then it's a function. I would say it passes as well. Despite I'm almost messed it up over here on the right, but it passes the vertical line test. Vertical line test meaning you can draw any vertical line and not hit the graph more than once. If you hit the graph twice, it's not a function. Okay. Inverses have to pass an extra test. Do you know what the extra test is? If you switch x and y, then from going this way, now you're going this way. The horizontal line test, this one fails the horizontal. Excuse me. It fails the horizontal line test, right? Because it intersects it twice. Now, let's be careful about what that means. It doesn't mean it doesn't have an inverse. It means the inverse is not a function. So it's still a function test, but instead of testing the function, you're testing its inverse. Instead of testing the original, you're testing the inverse. Let's see, and that's a quadratic or a parabola. Let's look at a cubic. Let's see. Something like that. You might even call that x cubed minus 1. It's not just x cubed, it's just been shifted down 1. So what do we think about vertical line test? Sure, passes VLT, vertical line test. So it is a function. I would say it passes the horizontal line test as well, right? Any horizontal line you draw is only going to intersect once. So it passes the horizontal line test. That means its inverse is a function. Okay, again, I think we've done this before, but let's do it on this one. To find an inverse, switch x and y, and then don't stop there.
And then you have to solve for x, right? Or y.
Solve for y. Yeah, it'll be solved for x when you make the switch, because you'll have x equals y cubed minus 1. So now we need to solve that for y, which is why we did literal equations a couple days ago, because hopefully we can we can get y by itself without too much difficulty there, which is why I don't mind picking on people. Ellen, what should we do first to start to get y by itself?
Cubic root or whatever it's called.
Not yet. I will need to do that.
Find one.
That's what we're headed for.
Yeah.
Nicole's trying.
Move the one.
Move the 1 over. You understand why we would do that? To start to get y by itself. So we'll move the 1 over by adding it to both sides. And then Ethan, what would we do next to cube root both sides? Because that'll undo the cubic. So cube root. And again, the whole point of cube rooting a cube is that they cancel each other out. And we've got y equals the cube root of x plus 1. Well, let's keep thinking about that problem. Preston, if I want to graph that, what is the change, what is the transformation to the parent function?
Left 1.
Good, left 1. So let's look back at our picture here. Let's go left 1. And then I don't have a grid, so this isn't going to be perfect, but I know I'll go over 1, up 1, down 1, back 1, and I can just kind of roughly sketch in the cube root of x plus 1. Or should I? So there's the cubic. And there's the cube root. And again, to find them, you switch x and y and solve for y. I think we mentioned this earlier. There's some sort of like symmetry going on with those two graphs. What are they reflected across? It's be careful, it's not reflected across x or y. Like if you fold that way, it doesn't work. It's reflected across a slant. Be careful, it's not a slant asymptote, but it is a slant. It's reflected across y equals x. Lots of practice. 20 years of graphing practice. Someday you too might be able to draw a straight line. That always happens. Your inverses and functions are reflections across y equals x.
Doesn't that have to do anything with that
No, but it's always a point where x and y are equal to each other. So there are some weird things happening at that point, but we're not really going to go that deep into inverses. F and F inverses reflect across y equals x, which I think makes sense because how did we find that inverse?
Flip x and y?
Yeah, and another way to say flipped x and y is we set x equal to y and y equal to x. So it maybe makes sense that that's why it's symmetric across y equals x. So we don't really do much with that, but it's kind of a verification. If you graph both of them, it ought to look like, if your graphs are decent, it ought to look like they are reflect across y equals x.
Is it the same if the original function is negative? Like if it was flipped?
Yes. Yep. They'll always be reflected across y equals x. So it's basically we just use that for a check. We don't like graph them based on that. That would be kind of tricky. But it is a nice check to at least visualize y equals x in there and see a little bit of symmetry, hopefully. Do you remember what we do to verify that things are inverses? to verify that f and g are inverses. Here we think about inverses as like undoing things, like inverse, reverse, undo. So if I take f of g of x, so we plug x into g, we get some answer, we plug that answer into f. If f and g are inverses of each other, if they undo each other, then whatever we plug in, g does something, f undoes something, and what would our output be? X. And so to show that things are inverses, to verify or show, or heaven forbid we use the word prove, you'll scare that word. We'll stay away from prove, even though it's the same thing as verify or show. We want to show that f of g of x equals x, and like the order doesn't matter. If you do f first and then g, you also get back to x. And you plug in x, that way you're sort of showing that it works for everything. Right? It would work for 2, but if you plugged in 2 and you got out 2, that would only prove that it undid 2. You need to check everything, so you plug in x as like a representative of anything. One more picture here. If you think of the function as like, see, this one, the g of x comes first. So we put x into this g of x box or function, and it does something. And then it goes through the f of x box, which undoes exactly whatever g of x did, and then that spits out x. That's what makes them inverses. G does something, f undoes it, and you get right back to where you started with. Okay, let's do a couple of examples together so we know what's going on here. So this is the worksheet, the assignment, but we'll do some together. Worksheet 6-2, inverses of cubes and cube roots. For each function, find its inverse, graph both the function and the inverse, and label them so we know which is which. Then use composition of functions. Guess we didn't call that composition a minute ago, but this f of g and g of f stuff, that's composition of functions is what that's called. You're composing functions together. You're not adding them or multiplying, you're composing them. Okay, so back to number 1. We got a lot of things to do with number 1, but hey, that's why we got half a page to do it. Do you want to graph first or find its inverse first? This doesn't really matter. I thought so too. That's not the order, but I agree. Let's graph it first. So we can pick on people, but we can only pick on the people who are here. It might be incentive to miss. I don't know. Allie, give me one of the transformations to that graph. What's that? Up 8. That's going to be fun to mess with. Up 8. Nicole, what else has happened to that graph? Left 3. And Cody, what else has happened?
Stretch by 2.
Whoops. Wait, what's not right? I took Nicole's word for it.
Oh, right 3.
Right 3.
Or you can make it left negative 3.
Yes, you could make it left negative 3. That would be very confusing. It would be accurate, but confusing. So I'm going to go with right 3. Okay, up 8, right 3. There's my new starting point. Normally we go 0, 0, 1, 1. Is this a 2, 8 or an 8, 2 problem?
2, 8.
Why 2, 8? Because you're cubing it, and 2 cubed is 8. Okay, so 1, 1, 1, 1.
But isn't it stretched? Yeah, it's
Oh, it is stretch. Thank you. Good catch. Stretch by 2. So 1, 2 on either side. And then 216. That's way off the page on the top end. Maybe we can get there on the bottom. It should be there. Because this is a 10 by 10, I guess a 20 by 20 grid. So let's see. I think it would be 2 from the bottom.
Yeah.
I don't want to count it all the way out. I want to do the math to figure it out. So there's the 216 point. It's annoying with my mistakes in pen there. So too much. Way too much. Way too much. There we go. Well, now it's not enough. There we go. Look at that. Surgical work with the whiteout. So super steep cube root. I can't draw on that because it's not dry yet. Messed that up. Okay, now I need to find an inverse so that I can graph the inverse. So Nick, what do we do to find inverses? Switch the x and the y. I guess this isn't a big deal, Megan, but there's not a y in this problem, so
The y is the s and the
yeah. So we'll call that x, and that will make y, and then everything else stays the same. And now I got to get y by itself. So I got to start peeling off the layers to get to y. So Rena, what should I do first? Move 8 to the other side. Leah, what do you want to do next? Divide by 2. We'll have to be careful with that when we get to it. Liam, what do you want to do next? Cube root. And lastly, Jackson? Add 3. I do not want to graph. I don't really want to graph that either. Except that I can kind of use the symmetry. Let's see, what in the world is... I'm going to maybe put the 1/2 out front. Not out front, because I didn't want to take the cube root of it, but out front of the x minus 8, because that's still a right 8 and an up 3 situation. Deal with the 1/2 in a minute. Right 8, up 3. Right 8, up 3. And normally we would go 1, 1, 8, 2 because it's a cube root. Okay, we got a 1/2 in there with x. Yuck. I don't think we can add it. I think the x stuff is always backwards, right? The minus 8 meant right 8. And so the 1/2 on the inside of that, instead of multiplying by a half,
Is it by 2?
it's going to multiply by 2. It's going to be the opposite of what you think. But that fits with the x stuff. The x stuff is backwards, right? Minus 8 means right 8. You don't even think twice about that. You just know it's sort of backwards. Well, it's the same if something's multiplied. So we're going to multiply the x's by 2. The good news is you realize, wait a minute, that's the same table we just had. You're like, yes, because we switched X and Y. And so if you get used to it, you don't even do that. You just like, oh, well, I'm going to just take those points and swap the order, and there we go. So from this new spot, I'm going to go right 2 and up 1. Down 2 and back 1. And then I want to go left 16, which puts me 2 away from the edge, conveniently enough, similar to this point down here. F inverse and F. And we don't have to draw the y equals x line. Maybe you can visualize it and be like, oh yeah, I did a pretty good job because those look like they reflect across y equals x. Okay, back to instructions. How are we doing here? Find its inverse. We did that. Graph both the functions. We did that. And the inverse. Use composition of functions to prove their inverses. Oh, we haven't done that yet. So let's call this second one g of x. And then I need to do f of g of x and g of f of x. You have to do both. It's annoying. We don't ever do problems where one works and one doesn't. So like if one works, they're both going to work, but you have to show both. So f of, this one's going to be lovely, half of x minus 8 plus 3. So that means that whole chunk of ugliness right there is now the input to the f equation. So it's going to look terrible when I first write it, but everything should work out. Like, what is our answer supposed to be? X. So it's one of those where you know what the answer is supposed to be, so even if you aren't exactly sure how to get there, students sort of fudge their way and hopefully land there. Okay, so in place of that x up here goes all of this stuff. Cube root 1/2 x minus 8 plus 3. Oh, yeah, you can see that. So I'm looking at the original function. I plug that in for x. And then there's a minus 3 and a cubed and a plus 8. So that looks terrible, but see what happens. The 3's go away first.
Is that parentheses supposed to be open after 8?
Good call. So what goes away first?
The 3's.
The 3's.
And then, yeah, like Ryan said, the cube root.
The cube root and the cube go away. Now let's be careful. I don't want to do like, some people are like, oh look, it all goes away, and they just write equals x. You're like, I mean, you know it's supposed to equal x, so like show me the steps.
Well, the 2 goes away as well.
And that's what you start doing it all in your head. You're like, oh, the cube roots go away, and then the 2's go away, and then the 8's go away, and I get x. Like, well, I know that you're supposed to get x. So show me a few steps in there. Cube and cube root go away, so that leaves 1/2 x minus 8. And then maybe I'm good with, the 2 and the 1/2 cancel. X minus 8 plus 8 is x. Hey, what do you know? We got what we were supposed to get. It's nice when you know the answer. That even happens in calculus. The most recent AP test we took, one of the questions was, show that the derivative equals. So it gives you the answer, you just have to show the steps to get there. Alright, we got to do this one more time. G of f of x is supposed to equal x. So g of 2 times x minus 3 cubed plus 8 because that's f of x. Now I go get the g function and plug in all of this stuff. Right, and it should be the same process. So cube root 1/2. Here we go. Here's x. All of this business. If I can fit it in there. 2 x minus 3 cubed plus 8. And then there's a minus 8 and a plus 3. Couldn't make it all fit. So it's a different order of canceling things, but it's still everything cancels. What's the first thing that cancels?
The 8 and 8.
The 8 and the 8. And what's the next thing that cancels?
Or the 2.
I think the 2's cancel next, so that would leave me with cube root x minus 3 cubed plus 3. Now it all fits on one line. Cube and cube root cancels. X minus 3 plus 3 is x, which is what we thought it would be. That's a long problem. Number 2 is kind of the same thing, so let's... Well, if you do odds, then you wouldn't get a chance to do one of those full length problems. What fun would that be? Let's look at number 3. For each function, find its inverse, graph them both, but you do not need to prove that they're inverses using compositions. So, yeah, it's the same as the first one, except you don't have to do the crazy algebra where everything cancels out. So, well, maybe we'll get through everybody today. We'll see. Logan, Dontre, and Reese. In order. Logan, what's one of the transformations that's happened?
Down 3.
Dontre, what else? Left 1. And Reese? Stretch by 2. Okay. Down 3. Left 1. Oh, maybe I should have started by remembering, whoa, that's why I should start, because I almost did a cubic rather than a cube root.
Oh, I did too.
So, not required, but that's why I like to do that on those parent function problems, like, slow down before you get lost in the trees, step back and see the forest. This is a cube root, so it should look like that. And I really almost graphed a cubic instead of a cube root. And Cooper was with me on that, so I'm in good company. Down 3, left 1, stretch by 2. Let's see. Whoops, I said cube root, so let's use cube root points. Stretch by 2. Not flip though, so over 1, up 2. Over 1, down 2 on the other side. Over 8. 1, 2, 3, 4, 5, 6, 7, 8. And up 4. 2, 3, 4. And then over 8. 1, 2, 3, 4, 5, 6, 7, 8. Oops, down 4. That's not the point. So yes, I've got a cube root, left 1, down 3, stretch it out. Okay, switch things up, so x equals 2 cube root y plus 1 minus 3. Goodness, like 4 steps to get y by itself, maybe? Question, Cole?
No, I figured
Sloppy handwriting. All right, Carson, I want to get y by itself. So what do you want to do first?
Add 3 to the left side.
Okay. Cole, what would we do next?
divide by 2.
So Again, I'm good enough to do 2 steps at once. I wouldn't try to do everything at once. Some of you would, and some of you would do it correctly, and others wouldn't. So don't do 4 things at one time. Ryan, what would we do next?
We cube each side.
Okay, and then Karis, after we cube each side, what would we do? Move the 1 over. So I'm going to cube and then subtract 1. So I was doing 2 steps at once. That's okay. 4 steps at once, inviting problems. Okay, so left 3, down 1, and that 2, what are we going to do with that 2? Same thing we did a minute ago. Multiply the x's by 2. Okay. Left 3, down 1, there's my new starting point. 0, 0, 1, 1, 2, 8. It's cubic, right? So I know basically what the shape looks like. And again, what do I do with this divide by 2 business? How do I adjust my table? It goes to the x's. And what does it do to the x's? Multiplies them by 2 because x is backwards. So 2 and 4. Again, hey, look at that. It matches our previous table. So over 2, up 1, back 2, down 1, over 4, up 8, 1, 2, 3, 4, 5, 6, 7, 8, and then back 4, down 8, I guess if I want to be fancy I could use a different color. Oh, that looks nice. Because what am I visually checking? When I say it looks nice, what am I looking at?
It looks symmetrical.
It looks symmetric with y equals x. Now again, if you don't graph enough points, or if your graphs are sloppy, it might not look perfect, but hopefully it looks like I graphed that one pretty good. So that one looks really good in terms of the symmetry. And then we're done with that one because we don't have to do the composition of functions business. 4 and 5, same kind of thing. 6, 7, 8, 9. Let's see. Find the inverse of each. That's easy enough. Write the domain and range of the inverse. But we talked about domain and range already. It's always all real numbers. Now when you switch x and y, that switches the domain and range. But if they were both all real numbers, and you switch them, then they're still both all real numbers. So all of that to say, pretty much all you got to do on that one is find the inverse of each, because domain and range is always all real numbers. Check by graphing on your calculator. I mean, if needed, I guess. Right? You would just graph it and look for that symmetry. But most of you are not going to. You're going to switch x and y and solve for y and trust that you did it right. And the only mistakes you will make is if you try to rush through it and do it all at once. Right? Some of you you're gonna do so many of these that you're gonna look at number 6. I wonder if I can do it. And say the inverse is going to be x minus 8. I shouldn't be encouraging this kind of thing. Over negative 2 cube root minus 4 equals y. But I'm not even convinced I did that right.
That's what I had. You did.
Minus 8 divided by negative 2 cube root minus 4 equals y. Yes.
That's right. Thank you.
So there's number 6. Done all in my head. Very dangerous. Don't do that.
I'm doing it.
I know you are.